Okay, thank you very much. Hello, everyone, and welcome to our introduction to quantum ecosystem. Here at the Aggregate Intellect. Thank you very much for joining us today. This is very special since we are so close to holidays. So thank you very much, everyone who could join us live. My name is Rezaee. I organize the quantum technology stream here at the Aggregate Intellect. Please, if you have any questions for André, put them in the chat box, and we will get to all those questions at the end of this webinar. I'm very, very excited today to host André König. André is an author, a speaker, investor, and entrepreneur. He's very much interested in deep technologies, including quantum technologies. He's the CEO of Interference Advisors, the leading data provider and advisory firm on quantum technologies, and the CEO of Entanglement Capital, an investment fund into quantum technologies. André is a publisher and chief editor at the leading quantum tech business magazines. He studied quantum computing at MIT and holds an MBA in economics from the University of Chicago, Booth School of Business, as well as a master's in business from AISCIENCE School of Management. He is the founder and chairman of One Quantum. One Quantum brings together quantum leaders from around the world in dedicated chapters. They have 3 chapters at the moment: a startup chapter, One Quantum Africa chapter, and the Women in Quantum chapter. Thank you so much, André, for being here.
The holidays certainly arrived early with that introduction, and thank you very much, Reza. Greetings from Miami to what's my last work call before the holidays, and I'm excited to share with you a little bit about quantum, introduction to the technology, a little overview onto the global startup and vendor ecosystem, and then we'll wrap up with a little bit on quantum machine learning and some resources that hopefully might be helpful to everybody.
Wonderful, wonderful. Thank you very much, André. Thank you. I'm a little bit jealous since I'm here in Ottawa and it's snowing real hard. So I bet you guys don't have the snow there.
We cold in Miami is when it's below 80s, and it's 82 today. So we're not complaining.
Wonderful. All right, I will start with a couple of fundamental questions for you, André, and I really appreciate if you can tell our audience that your perspective of these questions, so we can basically warm up and get ready to listen to you and to see your slides. The main question which we always have when we talk about quantum computation is, okay, so how is this different from what we have been doing for past more than 70 years? We have digital computing, and we hear a lot about the revolution that the quantum technologies might bring to the science and to the engineering of computation. So can you tell us more what makes it so special?
Einstein, when he first in some of his thought experiments came up with this idea of quantum mechanics or quantum physics, along with some of his colleagues, called it spooky. I actually didn't prepare any slides. I rather thought I'd share a few different online resources that you can access them as well. Here you see an image of Richard Feynman, who many consider the godfather of modern quantum computing. And one of his most famous quotes saying, "Nature isn't classical, damn it." So if you really want to understand nature or do a simulation of nature, you better make it quantum mechanical rather than classical, or what you just refer to as digital, Reza. And that's the type of problem that we hope to solve with the quantum computers. There are really 3 core concepts in quantum physics that we use in quantum computing. The first one, you probably all have heard about Schrödinger's cat, and Schrödinger's cat is kind of a metaphor for quantum superposition. this question, is the cat dead or alive? But you can't really open the box, right? What that really means in a more practical sense is that we have what we call a qubit, and a qubit is a mathematical space, a Hilbert space, in which whatever element we choose, and we'll talk about that in a second, to produce a quantum bit, this qubit, which is the equivalent to a classical bit, can be in a state of superposition. So rather than having a value of 0 or 1, the binary model that we're all very familiar with, that dictates the classical and digital age, we now have a stage of superposition where we can have any value between 0 and 1 at any time. And that's really just a mathematical distribution in this spherical space where we have elements that might be built on superconducting technologies, and those are computers being developed by IBM, Intel, and Google, are evolving. There are optical photonic approaches to building this qubit mathematical space. The largest company here, PsiQuantum, just raised $250 million a few weeks ago to build qubits and quantum computer on this principle. And then there are other approaches. Trapped ion is one that has made a lot of progress over the last 6 months, where you use ions and trap them in a field and create this qubit. So what we're hoping to do with quantum computers, and we have done it already, we'll talk about that in a second, is create these qubits where we represent a state of superposition rather than a binary state of 0 and 1s. And what that allows us to do is kind of create a probabilistic representation of all possible outcomes rather than a deterministic 0-1 representation of outcomes. And that's what Feynman referred to when he said, when you want to understand nature, you can't think classically. Because if you think about the weather, if you think about coming up with medications, drugs, very, very top of mind these days, if you think about building financial portfolios, these are not classical binary 0-1 computational problems. They are optimization problems, factorization problems, traveling salesman problems, and that's what we can represent with this qubit and this approach of superposition. Just very quickly, I mentioned that there are 3 core principles, superposition being the one. Entanglement is the second. Quantum entanglement basically states that these qubits that we create can be initialized in the same state. So whatever state you produce in this qubit space here, you give it an initial value, you can give that to a second qubit. And these qubits, albeit completely unrelated, they can be physically completely separated, will evolve in exactly the same way. So now we don't only have this statistical distribution of potential outcomes rather than 0 and 1s, we also have an exponential growth of these results because we're able to entangle one qubit with a second qubit. And if you entangle 2 qubits, then all of a sudden you have 4. You have this exponential growth, right? From 4, you go to 8, from there to 16, and so forth and so forth. So with every additional qubit, you have an exponential speed up in computation power compared to a linear increase in speeding power, calculation power with the classical machines. And the last, and then I'll give you, Reza, a chance to ask any questions. The last aspect is called interference. Interference is something that had been proven in an experiment represented in this graphic called the double slit experiment, where basically you have a light source that you see on the left. You have an obstacle with 2 slits in it, and you have a screen behind it. And now you're trying to observe where the light on the screen is being captured or reflected. And what you can notice on the right side is that you have this very distinct wave pattern of distribution. And what that basically says is that these light elements, photons, whatever it might be, before they hit this obstacle and the slit in it, they sort of already know where on the screen they'll be ending up, because they have a wave-like distribution on that screen, which is called interference. And just like when you throw a rock into a lake, a flat lake, and you observe the circles that it builds on the surface of the water, you throw a second rock, these waves, interference patterns, can collide and either cancel each other out. That's called disruptive interference, like those headphones on airplanes, or they can augment each other and thus produce even a bigger wave. So these three elements of superposition, entanglement, and interference is what make quantum physics, quantum mechanics so different from classical, which is what we use to build these qubits to hopefully solve very complex problems that cannot be solved classically, no matter the computational power that we're able to achieve.
Wonderful, wonderful. Well, that explanation brings us to my next question, which you mentioned. It gives us the power to solve specific types of problems that are classically very hard to solve. Can you tell us a little bit more about those type of problems? Basically, the question is, which areas of the science and technology you see they will be mostly affected, and these problems lays down, under those verticals?
And that is a very difficult question to answer, obviously. Mm-hmm. There is, the scientific physics community that says, theoretically, we can solve these types of problems. Then you have all the big users from Wall Street banks like Goldman Sachs, JP Morgan, to car manufacturers like my German friends where I'm from, BMW, Volkswagen, many chemical, pharmaceutical companies that are working on these and saying, we would like to solve X and Y, Z problems. So there's a lot of hype in the industry about what can potentially be done with quantum computing. As of today, and I'll exaggerate a little bit, that gives you, Reza, the opportunity to ask me more questions. As of today, we haven't solved any problems with it. We're just playing around. We have dozens and dozens of these quantum computers. They are not yet at the level where they are sufficiently powerful to theoretically solve a quantum problem, but we're getting very close to that. And every other week, you see a new research paper saying, we have come very close to solving this specific problem. So there's a lot of hype versus real facts in the industry. And this is my newsletter where I just 2 weeks ago wrote about that. So I encourage you, for those who are interested, to take a look at this, quantumcomputing.substack.com, quantum hype versus traction. But to answer your question, we actually have, and this is just a small extract of our database, a list of use cases that the industry side that I just mentioned is working on. And these are all, mathematically speaking, optimization, factorization problems, traveling salesman type of problems, prime factoring type of problems, etc. And you see here on the left side, this has many different business applications, from factory automation and routing, ad revenue maximization, chemistry simulation, new materials, weather modeling, asset management, risk management, high frequency trading, credit scoring, prime factoring. Many of you probably immediately thought about encryption. So this whole question of, can quantum computers break encryption is a very big field. We have pricing use cases, traffic flow optimization. The car companies I mentioned earlier talk a lot about optimizing electrical batteries, new sources of energies. All these are types of use cases that are being worked on. If you take more of an academic look at it, and this is a research note we just recently produced. Happy to share that with anyone. Just send me an email online or ask Reza for my contacts. There's really algorithmically only a certain the number of very specific problems that can be solved. You've heard me talk about optimization, prime factoring, things like Monte Carlo, machine learning, big data, and so far. When you start to match those kind of things against specific industries that might be struggling with these types of computational problems, from data companies to finance companies, logistics, telecom, biology, chemistry, operations, you very quickly, and this is a little small, let me see if I can make this bigger, you very quickly come up with very specific areas of potential use cases where we can see what we call a speed up over classical computing. For that, we not only need to improve the quantum computing hardware, but we're getting very close to that. We also, and in my opinion, most importantly, need to come up yet with new quantum algorithms that describe all of these challenges in a quantum-friendly way so that we can execute them on a quantum computer.
Wonderful. Thank you very much, André, for your insight into that question. It's very exciting, actually, to see all these possible use cases already are out there and being explored, and we all are waiting for that, practical, basically hardware to be available, so we all can see that quantum speed up. Okay, thank you very much, André. I think we are good for now, and please take it away, and we would love to hear your insight about quantum ecosystem.
Yep, let's look at who the players in this space are. This is one of the many websites I ran, the KISS Quantum Information Science data portal at kissdata.com, where we publish a lot of free data. We have a paid subscription of it, where instead of the 2018, you get the up-to-date data and all the details. But just so to give you an idea, quantum tech startups by country, this is from 2018. In 2018, there were roughly 250 to 300 startups working on quantum computing hardware coming out of the big university laboratories, or working on quantum computing software occasionally, but back in 2018 that was still rare, working on very specific quantum problems as well. Your new quantum-driven financial portfolio, your new quantum-driven drug discovery process, or whatever else it might be. You see the geographical distribution. Let me make that a little bit bigger as well. There you go. You see the geographical distribution. To no surprise, the US is the largest quantum tech startup ecosystem. Very notably Canada, where a gentleman by the name Rezaee, who's the founder of BlackBerry, for those of you who still know that, he invested 350 million of his personal money into the University of Waterloo and built a quantum kind of hub around it with several startups and accelerator and so forth. So Canada is a big country in that. Quantum also has a lot of national security implications, and you see Russia on the map here, but very light colored. That is only because it's very difficult to get reliable data out of Russia, which is true for China as well. But Russia, China, and the US really are considered, sort of in a quantum Cold War without being too dramatic, beyond the threats to potential encryption that we briefly touched on. And currently there's a big hacking incident that is being blamed on one of those two countries in the US, right? Quantum also has national security implications when you start to look at new materials that might be used for weaponry. airplanes, logistics, space, and so forth, but also telecommunication and secure communication. So the US, China, and Russia are the three big forces here. Australia has a couple very, very advanced research laboratories that started to spin out startups and vendors and build a very strong ecosystem. And Europe, actually, as an aggregate, if you take all of the European Union countries together, is even bigger than the US, being led by the UK, especially the University of Cambridge, Oxford, and Bristol, with a very large network of basic science research, but also startup spin-outs. Germany, in many sub-areas of quantum information science, when you look at the basic science, is actually considered a leader in the research. My home country, unfortunately, is a little less innovative when it comes to creating startups, funding these startups, and commercializing those solutions. And that is the same in France, in Spain, and Italy. The Netherlands is very strong. Finland is very strong. So altogether, the European ecosystem is very, very strong. And as of today, 3 years later, through the EU flagship program, unified and really one of the leading forces in the world. Latin America, Africa, as you see, most parts of Southeast Asia outside China, is kind of a quantum desert. India is just about to get on the map. Quantum tech startups, just a very loose distribution here. Quantum computing hardware, algorithms, software, quantum key distribution, which is this encryption aspect, quantum sensing, which uses properties of quantum entanglement and interference to build new types of sensors, which is very important in defense industries, obviously in energy and mining. Quantum communications, which is this whole idea of building unhackable, completely self-maintained communication networks. Those are the core areas of quantum information science. You see here the distribution. Most companies are active in quantum computing, hardware as well as software. And then there is a very steep drop to quantum key distribution, sensing, and communication, where you have much smaller ecosystems. It is a very white, male-dominated industry. We have a lot of data on that. We'll look at the funding in a second. I'm just checking if there's anything else that's interesting here, but maybe this is an opportunity for you to jot down questions that I can answer later. A couple of other quick things I want to show you here. Merely quantum computing hardware companies. So here we have 3 pages of quantum computing hardware companies. You see some of the big names, Alibaba Group, IBM, Google, Intel, and so forth, that are building quantum computers using different quantum computing modalities or architectures. So how do we build these qubits? Do we use superconducting technologies, trapped ions, topological, cold atoms, or photonics? Those are the big type of architectures. So there's roughly 60 or so companies that are doing that today. And there's a lot of small companies like Alice and Bob that just came on the scene 6 months ago, and is a spin out of a very large French Paris-based engineering school. Arca Materials, which is an Australia-based, publicly listed penny stock, but with amazing technology. D-Wave system, which you might have heard about, which uses a variant of quantum that's called annealing, which many say is not real quantum, but a very large company. So you have many of the big companies, Fujitsu, Honeywell, that are very, very strong, but you also have small teams, 4 people, 5 people, maybe 20 people, that spun out of a university and are currently working on it, just to give you a sense of what this universe looks like. Here we have another list with quantum computing software companies. interestingly to me, there are almost as many software companies as hardware companies in quantum computing. If you consider the stage of maturity of quantum computing, which is still very early on the maturity curve, I find that very interesting, and take that as a signal of how confident folks are in this technology, so that they already start to build real solutions before we even have hardware that is yet fully developed. So all these companies, you will only see a few big names like Baidu out of China, Cambridge Quantum Computing, probably the largest quantum computing software startup with roughly 80 or 90 people on staff. But the rest of this are small teams of 2, 3, 4, 5 developers with some seed funding, maybe a couple millions at most, working on specifically quantum software. We also track quantum algorithm companies, which are somewhat different in our opinion from software companies, because they have more of a focus on the actual math behind a potential use case rather than just writing the software. We looked at the use cases. Let's quickly look at the investment space. This is something I published 3 weeks ago. We looked at all the investments as of November 15th in quantum computing for the year, just to give you an idea. And these investments are relatively small. Total capital just above 1 billion US globally for the companies that we track. There were 2 very large deals in excess of 300 million. If you take these tail ends out, the rest of the ecosystem barely got $500 million in capital. That's a lot of money. At the same time, if you compare that to AI, other new technologies, it really is not very much. You have a breakdown by these quantum computing modalities or architectures. Yes, come in. Sorry, I've got somebody at the door. As well as sources of capital and capital targets. Just give me 1 second, a Christmas delivery. Yes. André. Perfect. Okay. Thank you so much. Okay. Gotcha. I'll run it down. Sorry about that. A little Christmas.
No worries.
Door.
If I can interrupt you for a moment, yes. André, since we are here, this is a good spot to ask. Do you think this is a good time for small startups who want to get into the hardware space or software space? Is a good time in terms of fundraising and talking to VCs, or how do you see that?
Yeah, you asked the tough questions. If you look at the sources of capital,
right,
the targets of where that capital is flowing, you notice that again is very restricted to these large geographies in terms of sources of capital, especially Canada, the US, Israel, and the UK. In terms of destinations, again, the US, Canada, China, increasingly the UK, and Finland. Outside of those geographies, these numbers get very, very small. I have another slide over here, which shows, and this was at the half-year mark of this year, all the investors in quantum. You see some early stage funds, seed funds, private angels, regional funds, and venture capital funds. So this is a very small universe. And my sense is that especially on the venture capital side, the more professional, somewhat larger checks, most of the firms that invest into deep tech or technology have made their bets. And many of them tell me, we're only looking to make 1 or 2 investments, then we'll observe it for a year or 2, and then we might make more in quantum. So if this is what you're looking at, I think it's going to be very, very tough. There's still a lot of regional money out there. Every big country has a very generous national or regional program. In Germany, in excess of 3 billion. In the UK, about 1 billion. And in the US, almost 2 billion. You see Business Finland in here. Business Finland, I believe, is 150 million. So there's a lot of regional money to be had, especially for early stage companies. Convincing angels and seed stage investors is very, very difficult. And the reason is all of this. This is so difficult to explain to an investor that it becomes very difficult to raise that money. So yes, it is possible, but it is difficult. And in my opinion, you need to have a very specific focus that differentiates you from the rest of this universe that we just looked at from all these companies. If you can do that, then I think you'll get money.
Wonderful. Thank you.
All right, where we are at. So that's the quantum tech ecosystem. Any other questions to that before we take a little look at quantum machine learning?
Well, actually, you mentioned Africa, and also I know you guys have the Africa chapter. We don't hear much about that, so it would be great if you can add a little bit detail about the quantum technologies in Africa.
Yes, Africa obviously is a little behind, unfortunately. There are a very small handful of very reputable universities, notably in South Africa, Wits University, but also in Egypt, maybe in Morocco. The United Arab Emirates, albeit not Africa, but they are, building a quantum technology center with a very generous grant of, I believe, about $1 billion US. So there isn't much in Africa itself, especially if you take the Maghreb countries out, the northern part, and go sub-Saharan, in terms of basic science that is able to flow into quantum technologies. However, thanks to companies like IBM, for example, that has a very large global community of developers, you can get free access to the IBM Quantum Cloud. With very limited calls and server time, of course. But you can play around on a quantum computer. They have great online resources, all the way to boot camps to teach you how to actually understand and program, if you will, a quantum computer. And there is a real community of that in Africa, especially Morocco, Tunisia, Egypt, but also South Africa. I have a small team up here in Zimbabwe, and thereafter. I think there are only 3 startups that we are aware of on the African continent in quantum. Our Africa chapter has 30, 35 members, and most of them are in academia and science, so still very small.
Great. Thank you so much, André.
So most of you, I imagine, are interested in artificial intelligence and machine learning. Quantum machine learning is actually a thing, QML. At the very basic level, machine learning neural nets are an optimization problem, right? So there's a lot of literature out here, and we'll just start very simple with a Wikipedia page here. But if you go into the research archives, this is really one of the big areas of focus for many companies, and we'll talk about that more in a second. It is also here, you see my little star rating system. One of the areas that is, of course, highly applicable when you look at the business problems, but also highly likely to develop the speed up over classical machines, or quantum advantage, as you could call it, to classical methodologies. Quantum can be applied to different fields in artificial intelligence, machine learning being one of them. It can also be applied to sampling technologies, techniques, to Markov models and a few other things. And we'll look at that in a second as well. This is a paper, and please email me or Reza. I'll email it to you. That is, in my opinion, the best summary of quantum machine learning. And again, it goes beyond machine learning. It is other artificial intelligence methodologies that apply. You have a very nice introduction of what resources are available and what the state of those resources is, as they refer to machine learning and other AI methodologies. This, by the way, is what we call a quantum circuit. So this is how you would talk to a quantum computer, right? Through a gate-based model. You have your qubits here on the left side, and then you basically tell them, very highly simplified, what you want them to do in this Hilbert space, where you want them to point, what spin, what kind of value you want them to have, and so forth. And that is how you build a quantum circuit that executes a calculation. So there are obviously, we said that these applications to quantum machine learning and neural nets, which basically optimization problems. There's been a lot of research done on Markov models, traffic optimization when you look at packages, Boltzmann machines, a lot of work on clustering, but NLP in general, a lot of work on natural language and everything that goes with that. So those are the main areas of application when you think about machine learning, quantum and artificial intelligence. Really mostly machine learning and natural language and everything that's kind of involved with that. And there's a real ecosystem of companies focusing on that. Just to give you a small excerpt of that, to our count, there are between 30 and 40 companies out of this entire ecosystem that have a stated purpose of doing quantum machine learning or NLP. Rezaee is one of the largest and very famous ones. They take it a step farther and say they want to solve specifically chemistry problems with quantum machine learning. I believe Rezaee raised roughly 20 million. You see they have partnerships with Microsoft, which has a quantum cloud, Amazon, which has a quantum cloud, QGAN is a European business network, various universities. So this is a very representative company when you look at quantum machine learning related applications. Another very, very large is not the doc here, but Zapata Computing, and this gentleman here, Christopher Monroe. Zapata Computing just raised 38 million. They raised roughly 15 million before that, so somewhere around 50 million total. And part of this raise of 38 million just a few weeks ago was a focus on quantum machine learning specifically. Before that, Zapata Computing was a quantum computing software company that would look at all types of quantum computing software. With this raise, these new investors and the new board they bring on, and you see some of the team here, they specifically focus on machine learning and how to solve those types of problems. So another company you need to know about, Cambridge Quantum Computing, I mentioned them earlier. They have about 100 people on the team. They have different technologies. They actually have a quantum compiler. There are 3 or 4 companies out there that are building quantum compilers. Ticket, Cambridge Quantum Computing's one, is supposedly the most reputable and reliable one. They have a quantum chemistry team. They actually have a quantum key distribution product called Iron Bridge. A lot of work on quantum finance, but something that they are working on is quantum machine learning, and actually more specifically, this is a little misleading, natural language processing. And about 6 months ago, they released a paper on natural language processing where they claimed a speed up over all known classical methodologies. They haven't been able to fully back that up in the peer review process, but at least they are getting very, very close to it. Xanadu, the full name is actually Xanadu AI. You see it here in the URL. Is another very, very famous company focusing on quantum machine learning. Their lead scientist, Maria Scholl, actually is out of South Africa, getting back to your question earlier, Rezaee. So another company that you should look at. And they have the distinct difference that they also do hardware, specifically photonic hardware. So they try to build these qubits that we talked about using photons, which have a lot of theoretical advantages in terms of scaling, but a lot of practical setbacks as well. And they are hoping to specifically optimize that, they call it penny lane, for quantum machine learning. So they are purpose building hardware for a machine learning use case, which is very unique. No surprise here, our friends at Google. Google builds superconducting quantum computers, and a little over a year released a paper which declared this famous quantum supremacy. So the point where quantum computers become more powerful than classical computers. That is still hotly debated today. But most interestingly, their quantum computing effort now called quantum AI. So this is a very strong signal. Google is very clearly building their quantum efforts around artificial intelligence, and in my personal opinion, focus not on the market and external users, but how they themselves can use it. Last item here. This is a paper that just came out December 7th, which was very well received in the industry, building GANs using trapped ions, so another of these architectures to create these qubits. And they were able to generate digits, images, just from the data. Obviously, one of the core tasks in terms of proving your worth, and they were able to create these images or videos from the GAN and build a QGAN, a quantum generative adversarial network, and yet another very recent claim of quantum speed up, advantage, supremacy, many different terms for it, but using quantum doing better than classical, and this one specifically in machine learning. So that's a little overview over quantum machine learning, natural language, and other AI applications.
Wonderful. Thank you so much, Andre. Thank you for all the information, the insight, and the resources that you introduced us. It was amazing. I was not really aware of this this last paper you showed. It's great. I just have a tiny comment, I think, about the Zapata computing. The gentleman name you mentioned is not Chris Monroe, is Alan Asper-Guzik. Yes.
Yeah. Yes.
Very nice. Thank you.
Somebody else who's very famous as well. He works actually at this ion trap company.
Yes. IonQ.
Yes, correct.
Wonderful. And Alan is here actually at the University of Toronto. Thank you so much, Andre. There are several questions posted in the YouTube channel, and I'm going to read them to you. And I really appreciate if you can tell us about your view and insight on those. Pankaj, I hope I'm pronouncing your name right, asks, Google claimed quantum supremacy. IBM disputed it. What's your take on it, André?
You'll probably be a little frustrated with my answer. I'm not going to answer if it was supremacy or not, and I'm not qualified to it. But there's a lot of money flowing into quantum. We looked at that a little bit, right? And we also looked at these national budgets of billions and billions of dollars that governments are spending on quantum. or somebody like an IBM, Google, Honeywell that are spending tens or hundreds of millions on their quantum efforts. So there's also a business side to it, right? And IBM, from an industrial commercial point of view, really created the quantum computing space. You know, nobody would be here today without what IBM has done. You know, then they have strengths, they have weaknesses and challenges like everybody else. But obviously, they are very proud and rightfully so about their work. Google came on the scene, had a fantastic team. They lost their lead researcher just a few weeks ago due to some internal politics, but probably the most renowned researcher who built a team around that, and specifically dedicated to making this quantum supremacy announcement, compared to IBM that would love to announce quantum supremacy, but is more concerned with building a quantum cloud service and a quantum cloud developer ecosystem. So competing interests, and I think that's where this comes from in terms of quantum supremacy or not. There's one kind of key word in the official definition, if there is one, of quantum supremacy, which is practical. The result has to be practical, and that's where this argument is about. Google says we gave a practical example of how to deliver a quantum result, and it's not able to be practically done on a classical supercomputer. IBM said, bullshit, pardon my language. They fired up all their supercomputers and were able to reduce the time on the classical machine so much that, in their claim, it became practical. That's what the debate is about. Beyond that, what Google did has no practical application for any use case. So that's another flavor of this practicality problem. Amazing work that they delivered. It has a lot of scientific impact. It's great for our community. To date, it hasn't delivered the type of result that we would need from a business or commercial point of view.
All righty. Great, great. André, I think Andreas provided a little bit more information regarding, I think, back to my question about Africa and the quantum ecosystem there. He mentioned there is a huge quantum community in South Africa in Witwatersrand. I hope I'm pronouncing this right. With startups and companies, even for quantum machine learning, there is a huge effort in South Africa. One of the main researchers, Maria Scholl, works at university. Okay, yeah, I know Maria, and she works, she's the lead scientist at Xanadu for quantum machine learning. Absolutely right. Andreas, thank you very much for providing us some further information. And then another YouTube user, MUU9, asked, which platform would you recommend, Andrea, for students who want to gain experience building and working with quantum machine learning and quantum chemistry models?
I am a terrible software developer, so very poorly placed to answer that question. But there are a few resources that you should know about. There is a company out there called StrangeWorks. Mm-hmm. We'll pull this up just so that you can get a look at it. And StrangeWorks will release a development platform very soon, but they have a very strong community, also on GitHub and Stack Overflow. So if you're really trying to get started, this is where you want to be. So go to StrangeWorks and quantumcomputing.com, join their developer community. Great, highly active space. I think they have thousands of members there. If you look at the cloud interfaces, you have IBM that we mentioned and their software platform, Qiskit. They have a main set of resources, from documentation to videos, boot camps, online, and everything else. They also have a lot of libraries So that is something that everybody should look at. Amazon launched their cloud offering just a couple months ago, and that's very interesting because it is fully integrated with all of the other AWS offerings, and you can pull, unlike IBM, from different quantum computing hardware. So check out Amazon. Microsoft has an online offering, and then there are a couple other smaller ones. Definitely start at quantumcomputing.com and strangeworks.com. Join their Stack Overflow, GitHub, and then check out IBM, Amazon, and Microsoft.
Wonderful, wonderful. Thank you very much, André. Just to add to that, there are other companies, including Rigetti, and as you mentioned, Xanadu. They do have platforms. They do have libraries that you can basically start working with. Okay, thank you so much, André. I know there are so much to talk about and questions that you may have. Please contact me or André directly. I'm more than happy to be the facilitator in this connection. André has so much experience in the field, and yeah, you should take advantage of all those knowledge and experience in quantum field. Thank you very much.
You can find me online if you're interested in quantum. Again, strangeworks.com, quantumcomputing.com. There's a blog called quantumcurious.org, which has a lot of getting started resources that are very interesting. If you're more interested in ecosystem, use case, business news, sign up to my newsletter, Quantum Computing. That's substack.com, and the data at kissdata.com. And you'll be smarter than many people in quantum already.
Wonderful. That's a great news. Okay, so you don't have to have a PhD in quantum physics to learn about quantum computing. Am I right, André?
We actually delivered a study to the White House about the workforce on quantum information science in the US, only in the US. Currently, 66% of folks working in quantum have a PhD. The rest, masters or bachelors in anything from physics, chemistry, philosophy, economics, and so forth. We had a conference last week with our One Quantum Woman in Quantum chapter, and we're joined by Anisha Mushti. She is 15 years old, a high school student, and started Community, a high school quantum community organization with over 1,000 members. She is absolutely fascinating and very impressive. So no, you don't need any of that. Start reading on some of these resources we shared, and then start messing around on IBM, Amazon, Microsoft, Rigetti, Xanadu. And the community is small and highly supportive. You'll get to know people fast.
Wonderful, great. Yes, she was pretty amazing at the 15 years age and high school student, right?
Yep.
Great. Thank you very much, André. I really appreciate your time and all the information, knowledge that you shared with us today. And thank you, everyone, all around the world on YouTube, LinkedIn, or on the Aggregate Intellect website, wherever you're watching us. Thank you so much. And we will have more of these quantum tech events scheduled for 2021. Please stay tuned. Follow us with on the social media and also on the Aggregate Intellect website for more details about those upcoming events. And I wish you a very happy holiday and a great year ahead. Thank you.
Merry Christmas, happy holidays. Stay safe out there.